Okay, we start. Okay. So welcome to the mathematical philosophy series organized by the Department of Philosophy at Peking University, in part to celebrate the centenary of Bertrand Russell's visit to China. I'm an alumnus of the Department of Philosophy at PKU, and it's my great pleasure today to host a talk by Professor Joe Halpern from Cornell University. Professor Halpern is a world-renowned computer scientist, and in particular, a leading contributor to the field of artificial intelligence, especially with regard to knowledge representation and reasoning. So his many numerous achievements and honors, for the sake of time, I will not recount here. Let me just say that Professor Halpern is a shining contemporary example of a distinguished scientist who also does at the same time does mathematical or exact philosophy. So my personal view is that three of the most important topics in philosophy are causality, knowledge, and rationality. Professor Halpern has made major contributions to the studies of all of them from using mathematical and formal tools. And today's topic is causality, which I think is especially fitting to this occasion. Bertrand Russell once famously advocated purging the philosophical vocabulary of the word cause, in large part because of its vague and misleading connotations. So I think he might have been very glad to see some regimentation of this notion, as we shall see today. So let's welcome Professor Halpern. Joe, please. The floor is yours.
Thanks a lot, Gigi. So as I told Gigi and Jing, I would prefer to have questions during the talk rather than just waiting until after the talk. And this is the kind of talk I suspect that I hope that will cause you to want to ask questions, both in terms, let's say during the talk, it'll be mainly for clarification. And I'm hoping somebody will be watching the chat link.
Yeah, that's right. I will watch this. So yeah, if you have any question during the talk, please feel absolutely free, and we encourage you to raise it right away. So you can either just raise your hand, I will unmute you, or you can type it in a Q&A if that's the preferred mode. Again, I will just remind Professor Joe Halpern from time to time about questions that arise.
Okay, that would be great.
Yeah.
So as Gigi said, I'll be talking about causality, and this is joint work with a lot of people, Judea Pearl, Hana Chockler, Chris Hitchcock. So let me get started. So defining causality is hard. We heard that Bertrand Russell wanted to purge it because it wasn't defined carefully. And it was so vague, but I hope to make it less vague in this talk. So many approaches have been considered in philosophy and legal literature for really two flavors of causality. What philosophers have called type causality, things like smoking causes cancer, and token causality, that's a statement like the fact that Willard smoked for 30 years is why he got cancer. So think of token causality as statements about individuals, and type causality as sort of more generic statements about properties of smoking or the relation between smoking and cancer. So why should we care? So look, type causality comes up a lot in statistics and science. Token causality tends to come up more in places like the law, although it comes up in computer science a lot too. I'll try to briefly mention that at the end of the talk. So here's an example. So I can say, look, it's true. It was pouring rain last night and I was drunk. I had way too much to drink, but the cause of the accident was the faulty brakes in the car. So of course, in the US, it's a very litigious society, and that's why I'm suing General Motors. So what does it mean to say that the cause of the accident was faulty brakes? Now, this is an example of something that arises in the law. The law cares a lot about causality because I want to say, because the brakes were faulty, they were the cause of the accident, and that's why I'm suing GM. Of course, historians and scientists are also interested in causality. By and large, statisticians are concerned with type causality, but they're also concerned with token causality. And as I say, we'll see it's relevant in computer science. So look, what does it mean to say A is a cause of B? why did Russell think it was so vague? Well, people have been trying to define causality for millennia. Arguably, this goes back to Aristotle, so I really mean it when I say millennia. The modern view arguably dates back to Hume. Actually, Hume gave two different definitions, although he thought he was just giving one, that have really started two tracks in reasoning, and one of them involved counterfactuals. And David Lewis perhaps was the first person to really make it more precise. And the intuition is that A is a cause of B. If A hadn't happened, B would not have happened. So notice the counterfactual here. If A had not happened, although it did, B would not have happened, although it did. So when I say that the brakes were the cause of the accident, I'm saying if the brakes hadn't been faulty, although I think they were faulty, I wouldn't have had the accident, right? So there's the counterfactual. And if I'm saying that the fact that I was drunk was not a cause of the accident, and the fact that it was bad weather is not a cause of the accident, I'm really saying even if I hadn't been drunk, I would have still have had the accident. They weren't the cause. And even if the weather had been perfect and I hadn't been drunk, I would still have had the accident. It's the brakes. If the brakes hadn't been faulty, I wouldn't have had the accident. So those are the kinds of things we say all the time in natural language. And that really is going to be the basis for the definition of causality, both for Lewis back in 73 and for the one that I'm going to give today. Now, notice, by the way, this example also illustrates the difference between type causality and token causality. As far as type causality goes, right, back here, smoking causes cancer. Well, it's true that pouring rain causes accidents, and drunk driving certainly causes accidents. But what I'm saying in this particular case, although in general drunk driving may cause accidents, in this particular case, the fact that I was drunk didn't cause the accident. I drive great when I'm drunk, right? So that's the difference between type causality and token causality. As a statement of token causality, it's true that drunk driving causes accidents, but in this particular instance, I want to say that drunk driving was not the cause. So I hope that's clear. So as I say, going back to Lewis, there have been definitions of causality that involve counterfactuals. Judea Pearl gave another definition that involved what he called structural equations and counterfactuals. I'll explain those in a few slides. And he and I gave a definition of actual causality using these structural equations, which I'll explain. Or actually, more accurately, we gave three definitions, or I gave three definitions. There was the first one that we gave in a conference called Uncertainty in AI in 2001. It was improved, that's a polite way of saying it was corrected, in 2005. Now, I should say by way of background, my PhD is in math, and I'm used to proving theorems. This talk will have no theorems. The problem isn't that I want to prove a theorem and I'm stuck on the proof. The problem is that I don't know what the statement of the theorem should be. So I'm going to give you a formal definition, so at least it won't be vague, and we'll get around Russell's problem. I'll give you a very precise definition of causality. I wish I could prove a theorem saying this is the correct definition of causality. And I would if I could, but I can't. I mean, the trouble is I don't know what it means to be the correct definition of causality. So it's very hard to state such a theorem formally. Now, we all have intuitions about what causality ought to mean, and there's lots and lots of examples in literature. So the typical way to argue that you have a good definition has been, oh, look at how well it does in all the examples in the literature that other definitions have not done so well on. And by and large, that's what I'll be doing too. So, when I say that we corrected our definition in 2005, that's because a student of Pearl's, Mark Hopkins, came up with an example that we all agreed was a very good example, and it showed that our first definition was not so good. So we came up with a second definition that dealt with that example. And then 10 years later, I came up with a third definition. And the history of that is that I was reviewing a paper, which shall remain nameless. I didn't think it was a very good paper. I really couldn't follow it. And then I thought, I had an insight. I thought this is what the paper was trying to do. I was wrong. That's not what the paper was trying to do. And I never did follow the paper. But that insight turned out to be useful because it led me to a third definition. And that's the one I'm going to give you today. So why am I struggling so hard? I mean, why do I need 3 definitions? Lewis had a definition in 73. There's my 3 definitions. There's lots of other definitions that people have given. Why are we working so hard? I mean, I said, look, causality is easy, right? But for that, A is a cause of B. If A hadn't happened, B wouldn't have happened. The problem is that so everybody agrees, if it's the case that but for A, that is, had A not happened, B wouldn't have happened. Well, in that case, A is certainly a cause of B. The trouble is there's other cases where we'd like to say that A is a cause of B when but for doesn't work. So here's a classic example due to Lewis. Suppose Susie and Billy pick up rocks and they throw them at a bottle. Now, let's say Susie throws a little bit harder. So her rock gets there first, it shatters the bottle. But let's also assume that Billy's throw is perfectly accurate. You can see that because Billy's rock goes right over where the bottle would have been had Susie's rock not gotten there first and hit the bottle and shattered it, right? So if the bottle were still intact, Billy's rock would have hit it. And we know that. So in particular, Billy would have shattered the bottle if Susie's throw had not preempted it. So what about but for? What can we say? Is it the case that if Susie hadn't thrown, the bottle would not have shattered? No. If Susie hadn't thrown, the bottle still would have shattered because Billy's rock would have hit it. So but for fails in this case. Now I can almost hear some of you thinking, all the way in Beijing, I can hear you thinking, well, I mean, suppose Susie's rock hit the bottle exactly at, well, for me, 8:45. Now it's true that Susie's rock is a but-for cause of the bottle shattering precisely at 8:45. Because if Susie's rock hadn't hit, yes, Billy's rock would have hit the bottle, but he would have hit it, let's say, 2 milliseconds later. So it would have shattered at 8:45 plus 2 milliseconds. So yes, it's true that Susie's throw is a cause of the bottle shattering at 8:45 and not at 8:45 and 2 milliseconds. But that's not what we say in natural language. I didn't ask, is Susie's throw a cause of the bottle shattering at 8:45? I want to say Susie's throw is a cause of the bottle shattering, period. That's what we say in English. And I want to capture that. And even if you really want to capture Susie's throw as a cause of the bottle shattering at 8:45, notice if you did that, oh, then that little gust of wind is also a cause of the bottle shattering at 8:45. Because had there been no wind, maybe Susie's rock would have gotten there a millisecond later. Maybe the wind made Susie's rock go a little bit faster. So now all of a sudden, we're going to get a whole bunch of other causes of the bottle shattering at 8:45, like the wind. And who knows, maybe humidity might have slowed it down a little bit. I mean, that has an effect on friction. So once you start worrying about sort of these very fine-grained things like the bottle shattering at precisely 8:45, you get a bunch of things being causes that maybe you never wanted to consider. So I'm really interested in the statement that Susie's throw is a cause of the bottle shattering, period. It's also a cause of the bottle shattering at 8:45, but I want to make precise the statement that Susie's throw is a cause of the bottle shattering. So intuitively,
just clarification.
Sure.
So were you just suggesting that what enters causal relations or token causality in any case is perhaps not totally extensional? I mean, it's not event per se, it's rather event under some description. Is this what you were advocating?
I'm willing to allow anything to be. I mean, so I don't think I'm advocating it so strong. It's not that and look, you might be interested in talking about Susie's throw as a cause of the bottle shatter at 8:45. I have no problem with that.
Yeah, but then that's sort of the same event under different description, right? Is that because
I'm going to avoid that problem.
It's the same event, but with different descriptions. So probably you are
saying, one or two events the same. I mean, I actually don't want to get into that can of worms.
Yeah, of course.
I'm going to preempt that and just stay with me and okay. I mean, I will give you precise formal semantics, but yeah. So let's keep going and maybe come back to the question if you don't feel I've answered it well. So again, the intuition is that why is Susie's throw a cause? Well, if Susie hadn't thrown, the bottle wouldn't have shattered, provided that Billy didn't hit the bottle. So that's going to be roughly the idea of our definition. But then why isn't Billy's throw also a cause? Well, I'm going to say, well, duh, as my kids would say, because he didn't hit the bottle. How are we going to capture that? So I need a formal definition, right? I don't want to be vague. So let me do a bit of a detour. I mentioned that Pearl used what he calls structural equations modeling, and I want to make that precise so that I can give you the formal definition. So the idea is that the world is described by a bunch of variables that affect each other. So Gigi, this is the beginning of the answer to your questions. I can have variables for anything. I can have variables that talk about Susie shattering the bottle. I can have a variable talking about the time is 8:45. And so I can talk about the event that Susie shattered the bottle at 8:45. So you decide your language, and it'll be each statement of the language, if you like, is an event. So formally it has semantics. It's a set of situations or something like that. And you get to choose what your language is. So you get to choose what descriptions you allow of your event. So I start with a language, not some kind of a primitive notion of events in the same event. That's not part of the formal framework. So bear with me, I'll make it completely precise. It'll be useful to split the variables into two sets, what I'm going to call exogenous variables and endogenous variables. And intuitively, the exogenous variables are the ones that I'm going to decide that's just the way it is. Why do people want to throw rocks? I don't know. They like throwing rocks. I'm not going to have variables that, let's say, I decide when I'm modeling the problem, I'll have a variable that says Susie threw the rock. I'm not going to have a variable that talks about why Susie threw the rock. I'm just going to say, well, she decided she wanted to throw the rock. That's just some exogenous feature. That's an exogenous variable that determines whether or not she wants to throw the rock. I'm not going to try to explain why she wants to go throwing rocks. I could have a richer model where I included psychological factors. I would have variables that talk about psychological factors. She's just, liked the idea of shattering bottles all her life. It's just adding more variables to the model, and it's up to the modeler to decide what the variables are going to be. So if you want to talk about time, go for it. Add variables in the model to talk about time, or have, if you like, timestamp variables. Bottle at 8:45, bottle at 8:46. That's perfectly okay. If you want to talk about, Susie's psychological state, by all means, have variables to talk about that. So it's up to the modeler to decide which variables go into the model. And as we'll see, our definition of causality is model dependent. So two different modelers that use different variables to describe what is arguably the same situation might get different answers when it comes to causality. I have a whole other paper that sort of discusses issues related to that, but that's certainly a property of the framework. Causality is a property of a model, and you can have two models that A is a cause of B in one model and not in another. And again, it's up to the modeler to decide which variables are going to be exogenous and which ones are going to be endogenous. But going on, it's called the structural equations model. That's because we have equations. And intuitively, we have an equation for each, I should have said here, endogenous variable. So for each endogenous variable, the ones that aren't exogenous, the ones I don't take their values as given, the endogenous variables, their values are determined possibly by other variables. So I can say if x is an exogenous variable, the value of x is y plus u. So once I know the value of y and the value of u, then I know the value of x, it's y plus u. It's given by this equation. Now, although I write an equal sign, think of this equal sign as more like an assignment statement in a programming language. So the fact that x equals y plus u does not mean that y equals x minus u. So I'm going to have an equation that says, for example, the bottle shatters if either Susie throws or Susie hits the bottle or Billy hits the bottle. I'm going to have equations that say that. But the fact that so that will mean if either Susie hits the bottle or Billy hits the bottle, then the bottle shatters. But the bottle might shatter even without Susie hitting or Billy hitting. And so if I tell you x equals y plus u and y is 3 and u is 5, that means x is 8. That doesn't mean that if x is 8 and u is 3, that y is 5. This is not equality like mathematical equality. This is more like an assignment statement. X gets the value Y plus U. That's perhaps a better way to think about it. All right, this is the only logic slide. I get my obligatory logic slide, but it's probably the most notation heavy slide, but don't spend too much time on this slide because it's really not what the talk is about, but let me make things a little bit precise. So we're going to reason about causality. We have the following language. We have primitive events that says capital X equals little x. So I can say, if I have a variable that talks about whether or not Susie throws, I'll say Susie throws is 1. You know, 1 says she throws, 0 says she doesn't. Here's the interesting statement. Notice I have X with an arrow on top. That's really view that as a set or a vector of variables. So it's X1, X2, X3. So what this statement is saying that after setting the variables in X, capital X to little x, phi holds. So think of this as if this formula is talking about the effects of an intervention. Intuitively, if I intervene and set X to 3, after doing that, phi will be true. So that's sort of the most interesting statement I can make. And I close off under conjunctions and negations. So I can say X is 3 and Y is 7. And it's not the case that Z is 2 or Z is 2, depending on where you learned your English. And this is the interesting statement saying after I set X to 3, phi is true. And now my semantics, I'm going to give these formulas a meaning in a causal model. A causal model is a triple that consists of 3 components. First, there's the exogenous variables and the endogenous variables. That's U and V. Remember, I said I take the variables and split them into exogenous and endogenous variables. And then I have a set of structural equations. And that's just these equations that I was talking about the previous slide, equations like this. So I have an equation for each endogenous variable. For each variable X and V, V is the set of endogenous variables, I have an equation like X is Y and Z. So if Y and Z are Boolean variables, I get values true and false. This tells me X is true exactly if both Y and Z are true.
I have a clarification question, Joe.
Sure, yeah, go ahead.
So you're saying these equations can be understood as sort of assignments, but
yes,
like in computer science, right? But
yeah.
For assignments, it's no problem to have cycles like X equals to X plus 5.
So in general, for the purposes of this talk, I'm going to assume that models are acyclic, that intuitively we have a DAG, a directed acyclic graph. So at the top, there's the exogenous variables. And then the next level, there's some endogenous variables whose values are determined by the endogenous variables. At the next level, I've got more endogenous variables whose values are determined by the variables above them. So if you know about Bayesian networks, think about like a Bayesian network.
Yeah.
In general, I allow cycles. So in my book or in the paper, I allow models where there are cycles. For this talk, let me assume there are no cycles.
Okay. But
so,
this will also affect the so-called logic or other stuff.
Yeah,
right?
it does. So I mean, I have axioms that hold if they're, an extra axiom. I'm not going to talk about axioms in this talk, but in the axiomatization for this language, there is an extra axiom that captures acyclicity. So it's really, I have all the axioms that I had, and then I have one more axiom that captures acyclicity. So, so again, I don't want to go there in this talk, but it's been done. I mean, it's so for this talk, you should assume that there are no cycles, that if I have an equation that tells me the value of X in terms of Y and Z, there's no the equation for Y does not mention X. So if X depends on Y and Z, then Y will not depend on X, right? So here's the semantics. So because I'm assuming that there are no cycles, so U is what we call a context. So U is a setting of the exogenous variables. Think of those as at the top of the DAG. They're the ones whose values determine everything else. So once I've got this acyclic structure, no cycles, once I tell you the values of the exogenous variables, the ones at the top, that determines the values of all the other variables. I hope that's clear. So again, I need to be a bit more complicated, but it's been done in the case of when I have cycles that I'm looking at fixed points, but let me not go there. But in the acyclic case, I'm going to say Y is equal to 7 if y equals 7 in the unique solution to equations given the context u. So u tells me the values of the variables at the top of the DAG, and that forces the values of everything else. So given this setting, this context, that determines the value of y. So that's what it means for y to be 7. Y is 7 if when you set the variables at the top to whatever value is given in u, that forces y to be 7. So hoping that's clear. If not, this is a good time to ask questions. So Gigi, are there any questions? Okay.
I don't see any.
All right, so here is the interesting statement. If I intuitively, if I intervene and set x equals to 3, what does it mean that phi is true then? Well, what it means is, let's look at this new model, m with x set to 3. I'll explain that in a second, but I'm going to say that this formula is true in the model m, if in the model where x gets set to 3, with the same context, the same u here and here, phi is true. So this is really going to be saying after you set x to 3, that changes the model. It changes it to this model. I'll explain this model in a second. And to say that after you set x to 3, phi is true, is just saying phi is true in this new model you get when you set x to 3. And what is this new model? Well, it's very simple. This is the new model that's just like m. The only difference is in m, I had an equation for x, for all the variables well, this is a set of variables. So in m, I had, right, as part of my set of structural equations, I had an equation for each variable that's in this set. I throw out those equations and replace them by the simple equation that says x gets 3, or whatever little x is, right? So this model m where x gets x is just like the model m, except that I throw out the equations that I used to have for x in this model m and replace them by a new equation that just says x gets 3. So now I have a new model, and I can ask if phi is true in the new model. And roughly this is saying, look, if you've intervened and set x to 3, I'm going to look at the new model where x is no longer determined by the equations that you had in m. It's determined by the equation x gets 3, because x was set to 3 by your intervention. And I can ask if phi is true in that new model. So again, let me ask if that makes sense. Any questions? All right, that's the logic slide.
Excuse me, how do you interpret negation?
How do I interpret which?
Negation.
I didn't understand.
Negation. So negation, yeah.
Sorry, one more time. How do I interpret?
Negation, not.
Oh, negation. Oh, no problem. So I can put negation anywhere. I close off under negation. So the negation of a formula is true. It's classical negation. The negation of this formula is true if the formula isn't true. So if it's not the case, the phi is true in this model. So it's really classical negation. Or the negation of this formula, if this formula says y is 7, it's not the case that y is 7, means y gets a value other than 7 in the context u. So it's just absolutely classical negation. And likewise, and or get, when I say close off under conjunction negation are interpreted classically. Nothing special.
Okay, thank you.
Here's another question regarding the semantics. Can I understand it under dynamic logic, where you determines a particular set of possible worlds?
Yeah. You can view this as a dynamic logic of causality, if you like. That this is the dynamic part. I'm in some sense changing the world, actually I'm changing the model, but I'm keeping the context. So it's just like, you might think of this as a program. After I run this program, phi is true, well, my program is intervening on x. So there is a sense in which this can be viewed as a dynamic logic. Yeah. That's not an unreasonable view.
So is there some extra benefit, epistemic, heuristic, or any other, if we think in this way or in another way?
I don't know that there's a huge benefit. I mean, certainly if you look at some of the axioms, they have the flavor of dynamic logic axioms, but a bunch of others don't particularly. I mean, it's not a very standard dynamic logic, so I can't hurt. So you get things like, box phi, and box phi implies C implies box C. So you get, I mean, again, you get some axioms like you do in modal logic. This is in the acyclic case, this is deterministic. So it's the case that not x gets x phi is true if x gets x not phi is true. So you can take the negation that was out here and put it in here in the acyclic case, not in general. So yeah, I mean, if it helps you to think that way, it's not a terrible way to think. I think in terms of causality, the better way to think about this is you're asking the question, if I were to intervene and set x to 3, what would happen to phi? Would phi be true? Right, so it's syntactically, it looks a little bit like a dynamic logic, but I'm not sure that's the best interpretation.
Okay, yeah, thank you.
Arsonists. So let me just give you some examples of how this works. So we have two arsonists that drop lit matches in different parts of a dry forest. Both cause trees to start burning. So let's look at two scenarios. One I'll call the disjunctive scenario. So all you need is one match to get the forest to burn. The conjunctive scenario says you need both matches. So, you know, a match starts a little fire, just one match will start a little fire that will die out. But if you have both matches dropped, then that'll start a big fire and forest will burn. So we can capture the difference between the scenarios using a causal, well, first, let me say that I can describe qualitatively what's going on using what's called a causal network, which is like a Bayesian network for those of you familiar with that. Intuitively, the U at the top is an exogenous variable. In this case, I have two variables, ML1 and ML2, that says, ML1 says arsonist 1 drops a match. It's a binary variable, either 0 or 1. He drops it or he doesn't. True or false, he drops a match. ML2 says the second arsonist drops a match. U you can think of as a variable that determines whether or not they drop a match. Maybe, you know, why do they drop matches? They were brought up in a house of arsonists, I don't know. So these are the external factors that determine whether or not they drop the match. Maybe they won't drop the match if they see a policeman coming along. So the context would tell you all of these external factors that, like, there's a policeman coming, so I won't drop the match, or there's nobody there, so I'll drop the match. Anyway, that's the U, the ML1, ML2. Finally, we have a variable FB that says the forest burns. And each of these variables have equations, and the most interesting equation here is the equation for FB. And this is how I capture the difference between the disjunctive scenario and the conjunctive scenario. In the disjunctive scenario, FB is ML1 or ML2, disjunction. In the conjunctive scenario, it's ML1 and ML2, the conjunction. So this is saying the forest burns down if either one drops a match, and this is saying the forest burns if both drop a match. So the whole point here is this is how I would capture the difference between the two scenarios using this framework. Questions? Right. So I want to define A as a cause of B in a model and a context in this pair MU. So intuitively, I'm assuming that all the relevant facts are given. I'm given the model. So the model will tell me how does causality work, intuitively what causes what. And the context tells me all the facts that are true. So the model might tell me, for example, does smoking cause cancer? Well, if smoking causes cancer, I would have a variable connecting smoking and cancer and saying, yeah, if you smoke and some other things happen, then you get cancer. Or if you don't think smoking causes cancer, that's okay. I would capture that in the model too. So the structural equations are basically intuitively talking about the effect of one variable on another. So that's a large part of causality. And the context is telling me what actually happened, saying, well, you in fact smoked for 30 years, or in fact, it was raining yesterday. And in fact, the brakes are bad. And in fact, the weather was bad. And in fact, you were drunk, right? So the context tells me that. Now, so I want to define what it means for A to be a cause of B. For A, I'm only going to allow conjunctions. It makes life a lot more complicated if I have more things other than conjunctions being causes. And which I usually abbreviate this way, right, using the vector notation. For the B, the thing that can be caused, that can be anything, an arbitrary Boolean combination. But I am going to restrict to non-modal formulas. So it's an arbitrary Boolean combination of these primitive events. So I'm interested in statements like the fact that x is 3 causes y to be 5 or z to be 2. All right, here's the formal definition. So I'm going to say that M is a cause of phi, given context MU, if, so there are 3 clauses, and the first and third are pretty standard, and all the work is in the second clause, which is in the next slide. So the first clause says, I would never say that A is a cause of B unless A and B actually happened. I mean, if you just think about natural language, I wouldn't say that Susie's throw caused the bottle to shatter if Susie didn't throw a rock and the bottle didn't shatter. We just don't do that in English. So I'm going to insist, if you want to say that x equals little x is a cause of phi, that both x equals x and phi are true in this model, in this context. AC2, as I said, is complicated. I'll stay tuned for the next slide. And AC3 is just a minimality condition. I'm not going to say that x equals 3 and y is a 5 and y equals 5 is a cause of phi if x equals 3 is already a cause of phi. So AC3 says this big conjunct shouldn't have any irrelevant conjuncts, because if it has irrelevant conjuncts, I should just prune them away. So I don't want dropping a match and sneezing to be a cause of the forest fire if dropping a match is already a cause of the forest fire. Does that make sense? I mean, I think that's pretty non-controversial. So all the action is happening in the AC2. As I said, AC2 is complicated. Here it is. I'll explain it. All I can tell you is this is the AC2 for my third paper. The AC2 in the first 2 papers was much more complicated. So if you don't like this, you for sure wouldn't have liked that either. So what's the condition? So ignore this W for a second. If we just ignore this, the part in blue, ignore it. Let's look at this part. I claim this is the standard counterfactual definition. It says there's a setting x prime of the variable x, and again, forget this part, such that if x, and forget this part, this is just the counterfactual. If x had a different value, in fact, x is little x, but suppose x were x prime. If x had a different value, then phi wouldn't occur. So that's the counterfactual. I'm going to say that x is 3 is a cause of phi. If it's the case that had x been 5 instead of 3, then phi wouldn't have happened. So I'm going to, right? So that's the counterfactual. X is a cause of phi. If x hadn't happened, then phi wouldn't have happened. If x had a different value, then phi wouldn't have happened. That's the straight counterfactual. And what I've added to that is this extra clause. I'm allowed to choose an arbitrary set of variables W. The fact that there's a vector here says it's a set of variables, endogenous variables in V. I'm going to fix them at their actual value. So suppose in the actual situation, W had the value 2. So now I get to say, well, suppose X were set to 7 instead of 3, and we fixed W at 2. Well, in that case, phi wouldn't have happened. So this is where I'm going beyond the standard counterfactual definition. I'm saying if X had a different value, and oh, by the way, also if you fix W to its actual value, then phi wouldn't have happened. So what do I mean by the actual value? Well, I'm looking at what happened in fact to the variable W. And this is only interesting if changing X to X prime would have changed the value of W. And I'm saying, no, keep W at its actual value. Even though you changed X to X prime, keep W fixed at little w. And in that setting, see if phi would change value. Now that's going to be hard to follow or to make sense out of until you see the examples. So let me now just say, if you understand formally what's going on, even if you haven't got a clue of why it's interesting or why I'm bothering to do this, then let's keep going. But if you have any questions formally about what's going on, then this is a good time to ask.
Does W appear in 5?
It might. I'm not preventing it from appearing in phi.
Okay.
I see. Other questions?
I also have a clarification question. So there is no like extra constraints on whether this W is sort of maximum, minimum, things like that?
No,
No, not at all. Just
not at all.
there exists such
So the
a,
X has to be minimal. Right?
yeah,
You
sure,
can't-
sure. But the
but the
W,
W can be arbitrary.
okay.
If W were empty, then we would have the
Yes.
standard counterfactual definition. So literally, if
Sure.
W were empty, so there is no W, just imagine it's not there, then I have literally the counterfactual definition, the traditional one. If X had a different value, phi would be false, right? So this
Right.
is sort of this is where I go beyond.
Yeah, but then it depends on the choice of your W, whether
Yeah, but there's an
can
existential
change the-
quantifier here.
yeah.
So all
Yes.
I'm saying, as long as there exists a W, then I'm going to say X is a cause of phi,
Mhm.
right? So
Okay, thanks.
now I saw some other questions not among the people I'm seeing in front of me. There was a ketchup bungu or something like that. I saw some hand raised. That's not somebody I'm seeing on my screen.
Not now, I think. We don't see the
Yeah, we don't see any.
hand.
Okay, so if somebody else has a question, then feel free to raise your hand or ask. All right, I'm going to keep going. Let me give you some examples. This will, I hope, make it clear. So let's look at the arsonist example. So first, let's start simple examples, but then I want to go to the Billy and Susie throwing rocks example, where you really see the power of the W. So first, the easy case is the conjunctive scenario. In that case, it takes both matches to start the fire. So in that case, I would say both ML1 equals 1 and ML2 equals 1. Each of the arsonists is a cause of the fire, of the forest burning down. They're actually but-for causes. If either one hadn't dropped the match, then the forest wouldn't have burned. That's easy. But the point is, this shows that an effect can have more than one cause. So each of ML1 equals 1 and ML2 equals 1 separately is a cause of FB equals 1, right? Because if either arsonist hadn't dropped the match, then the forest wouldn't have burned down. Does that make sense? Interestingly, in the disjunctive scenario, the conjunction is a cause. So the conjunction is not a cause here, just each separate conjunct is a cause. And this is the minimality engine, that I don't want the conjunction to be a cause because each conjunct separately is already a cause. In the disjunctive scenario, I'm going to need the conjunction because intuitively I have to change both ML1 and ML2 for the outcome to change. I have to set both of them to 0 for the outcome to change. ML1 equals 1 by itself is not a cause because if you keep ML2 fixed at its actual value, in other words, if the second arsonist drops a match, there's nothing the first arsonist can do that can stop the forest from burning down. Now, this seems a little bit strange if you think about it. So, in English, if I tell you we've got these two arsonists, all I need is one match to start the fire. It seems like I would want to say each arsonist is a cause, not the conjunction. So in fact, in natural language, I think what we do is, if you have a conjunction being a cause in natural language, we tend to think of each of the conjuncts as being a cause. So here I talk about each of them as part of the cause. And I think part of the cause is really corresponds more closely to what we call the cause in English. But I guess that's a matter of how we interpret natural language. But let me keep going to more interesting example, the Susie and Billy. So now we've got Susie and Billy both throwing a rock and the bottle shattering. If you take the most naive language, most naive model, where the only variables are Susie throws, Billy throws, and the bottle shatters. And here's the model. Susie throws, Billy throws, and let's assume for simplicity that the bottle shatters if either one of them throws. So I'm sort of building into the model the assumption that they never miss. I can have a more complicated model where in some contexts they both would hit, in other contexts just Susie would hit, sometimes just Billy would hit, sometimes neither one would hit. That's a richer model. Let me not go there. The point I want to make already comes up here. in this model, this is like the disjunctive case in the forest fire. If either Susie throws or Billy throws, the bottle shatters. Susie and Billy are completely symmetric. So in the story that I told you, I said, look, Susie throws, she throws a little bit harder, her rock hits the bottle, Billy's rock doesn't hit the bottle. And I'd like to say Susie's the cause and not Billy. In this model, Susie and Billy are completely symmetric. They both throw, the bottle shatters if either one of them throws. I would argue this is so in this model, they're both causes, but I would argue this is a bad model. Right? I mean, causality is relative to a model. There's nothing stopping you from having a bad model, but I would argue this is a bad model. Why? Well, it doesn't give me the answer I want, but more importantly, there's important aspects of the story that are not captured in this model. In particular, the story said, Susie threw a little bit harder than Billy, or maybe a little bit earlier, it doesn't matter, but her rock hit the bottle and Billy's rock didn't hit the bottle. So if you just take this model, you're not capturing the fact in the story that Susie's rock hit the bottle and Billy's rock didn't hit the bottle. And a good model would have to capture that. Now, there are many ways of capturing that. You can have timestamp variables. So you can look at the bottle at time 1 and the bottle at time 2 and so on. That's not how I'm going to do it, but I'm not trying to say that the way I'm going to do it is the right way. There's lots of ways of doing it. So for example, here's one way of doing it. I'm going to add 2 more variables. One says SH for Susie's rock hits the bottle, and BH says Billy's rock hit the bottle. And I'm going to bake into the equations the fact that Susie hits and Billy doesn't. Again, I could have a richer model where I didn't do this, but let me do it this way just for simplicity so I can make my points. So the equation is going to say Susie hits if Susie throws, but Billy hits only if Billy throws and Susie doesn't hit. So if Susie, so the equation for BH is going to say BH equals 1 only if BT equals 1 and SH equals 0. Because if Susie does hit, then the bottle shatters before Billy's rock hits it. So the only way that Billy's rock hits the bottle, according to this model, is if Billy throws a rock, he can't hit the bottle if he doesn't throw the rock, and Susie's rock does not hit the bottle. Okay, so that's my model. I'm not writing down the equations, but I'm hoping you can see. So the equation here would be BH is equal to BT and not SH. Billy hits if and only if he throws and Susie doesn't hit. Whereas the equation for SH is just SH is ST. If Susie throws, Susie hits. Right, so this model is capturing the asymmetry between Billy and Susie. In this model, Susie hits, but Billy doesn't. Now I want to say in this model, Susie's a cause and Billy is not a cause. And this is where I use the richer definition with the W. So now I'm going to take the W to be BH, and the value for W is 0. I'm going to keep BH fixed at its actual value, BH equals 0, because that's what happened in the real world. In the real world, ST and BT were both 1. SH was 1, Susie hit. BH was 0, Billy didn't hit the intact bottle. And BS is 1, that's what happened. So I'm allowed, according to my definition, to fix BH at 0. That's because, so the W here in this definition, the W is now going to be BH. I get to choose it, Yanjing, so I'm choosing W to be BH. And I fix BH at its actual value, which is 0. And in that case, if Susie doesn't throw, that's the counterfactual. In the real world, she threw, but if she didn't throw, and we fix BH to be 0, then the bottle doesn't shatter. So we get the counterfactual. But note, this is inconsistent with the equations. The equations would normally say, look, if Billy throws, which he does, in this context, Billy throws, and Susie doesn't, and if Susie doesn't throw, then Susie doesn't hit, Billy should hit. but I've intervened and I'm just making sure that Billy doesn't hit. So if we fix Billy at not hitting and Susie doesn't throw, then the bottle doesn't shatter. So according to the definition, this makes the fact that Susie threw a rock a cause of the bottle shattering, because if she hadn't thrown and we kept Billy fixed at not hitting, then the bottle wouldn't have shattered. Okay? But Billy's not a cause. It's asymmetric. We can't play the same game and switch the roles of Billy and Susie, because in the actual world, Susie does hit. And if we fix SH to 1, well, then the bottle shatters no matter what Billy does. So we can't just replace S by B and B by S. We can't reverse the roles of Billy and Susie here to get this same thing happening and show that Billy's a cause, because Billy didn't hit the bottle. Duh. So this is where I'm capturing the fact that, remember back here, I said I want to capture informally the fact that why isn't Billy's throw a cause? Because he didn't hit the bottle. So in the actual world, BH is 0, not 1. That's where I'm capturing the fact that Billy didn't hit the bottle, and that's why I'm using it in the definition. So are there any questions about that? So here's where I'm really using the definition, and this is the W.
Joe, a question?
Yep.
So in this kind of modeling, it's effectively reducing what Lewis called a case of late preemption to actually a case of early preemption, right? It's basically just saying there's no distinction there anymore. Right. I think he used this example as a case of what he called late preemption, where there's no cutting, right? Yeah, we model this way, there's still cutting, so cutting of the process. So it's a case of early preemption.
I guess you could think about it that way. I guess that wasn't how I was thinking about it, but that's okay. I'm okay with that.
Yeah, but then I wonder what do so. I don't quite remember how you handle the trumping, because when you do the case of trumping, right, it seems that you won't have any intermediate variable in between.
So we do handle that. I mean, I do that in the paper and the book. Let me not go there now, because I don't want to go. I mean, I'm already getting close to 9:30 as it is, and I have quite a bit more to say. That, let me just say very briefly, it matters very much how you model things and what variables you choose. So you're thinking about the example with the sergeant and the major. So we handle that, and so I'll refer you to the paper. We can talk about it afterwards, but there it turns out to very much depend. Just like here, if I model things this way, Susie and Billy are both causes. If I model things this way, Susie's a cause, but Billy is not. And it'll be the same thing in the trumping example, similar phenomenon. Let me look at a few more examples. And there's quite a bit more I want to say. So I'm afraid, I mean, it's okay. As long as I finish by 10, I'm okay, right? Or for you, I guess it's by 11. That's okay? It's an hour and a half altogether.
Yes, it's okay, because we have all kinds of questions during the talk. So yeah, sure.
Okay. So let me give you an example due to Ned Hall, who's a philosopher now at Harvard. Billy contracts a serious but non-fatal disease. He's treated on Monday, so he's fine on Tuesday. But had Monday's doctor forgotten to treat Billy, it's okay, there's a backup. Tuesday's doctor would have treated him and he would have been fine on Wednesday. The catch is that 1 dose of medication is harmless, but 2 doses are lethal. So if both doctors treat him, he dies. Now, in fact, the right thing happened. He was treated on Monday by Monday's doctor. Monday's doctor noted it in the record. Tuesday's doctor read it, saw that Monday's doctor treated him, so he did not treat Billy. And so Billy's fine, just as we would hope. Now, is the fact that Tuesday's doctor didn't treat Billy the cause of him being alive and recovered on Wednesday? And the answer is surely yes. So we allow, if you like, non-events to be causes. We don't distinguish between sort of the default event of not treating and the event of treating. It's just, this is a straight but for. If Tuesday's doctor had treated Billy, in this context, where Monday's doctor also treated him, he would have died. So the fact that he didn't treat him is a cause of him being alive, because had he treated him, he would have been dead. But let me point out something even stranger, perhaps. So let's model this carefully. So we have, ignoring the exogenous variable, we have 3 endogenous variables. Monday's doctor treats him, yes or no. Tuesday's doctor treats him, yes or no. And then we have another variable, Billy's medical condition, which has 4 possible values. 0 BMC equals 0 means he's okay on Tuesday and Wednesday. Intuitively, this is the case if Monday's doctor treats him and Tuesday's doctor does not, right? Then he's okay on Tuesday because Monday's doctor treated him and he's still okay on Wednesday. BMC equals 1 if he's sick on Tuesday and okay on Wednesday. This is what happens if Monday's doctor forgets to treat him, but Tuesday's doctor does treat him. So he's still sick on Tuesday because Monday's doctor forgot to treat him, but now he's recovered on Wednesday because Tuesday's doctor treated him. BMC equals 2 is the case if Billy is sick both Tuesday and Wednesday. This happens if neither doctor treats him. Now, finally, if both doctors treat him, then he's okay on Tuesday because Monday's doctor treated him, and he's dead on Wednesday. So here are the 4 possible values of the variable BMC. And we have the obvious equations. I actually just told you the equation for BMC. I literally gave you the conditions for under which BMC is 0, 1, 2, and 3. For example, BMC is 3 exactly if MT is 1 and TT is 1. Right. But notice I also have an equation for TT that says TT is 1 if MT is 0. So TT is, the equation for TT is it's not MT. Tuesday's doctor should treat him if Monday's doctor doesn't treat him. He should not treat him if Monday's doctor does treat him. That's what we want. That's the equation for TT. Right, so that's the model. What can we say about causality? Well, as I said, Monday's doctor treating him, well, I didn't say this, but let me say, Monday's doctor treating him is a cause of Billy being okay both Tuesday and Wednesday, and of Tuesday's doctor not treating him, right? Because if Monday's doctor treats him, the equation says that Tuesday's doctor shouldn't treat him, and it then follows that because Monday's doctor treats him and Tuesday's doctor doesn't, then Billy is okay both Tuesday and Wednesday, BMC is 0. Now, Tuesday's doctor not treating Billy is a cause of Billy being alive on Wednesday. Billy being alive is just not being dead. So it's either, BMC is either 0, 1, or 2. It's not 3. 3 is the one time that he's dead. So this is just what when I say Billy's alive, that's just this. But notice that Monday's doctor treating him is not a cause of Billy's being alive, because there's no way I can satisfy the counterfactual. If Monday's doctor doesn't treat him, no matter what Tuesday's doctor does, Billy's going to be alive. The only way Billy's going to be dead is if Monday's doctor treats him and Tuesday's doctor also treats him, right? So there's no way I'm going to get the counterfactual condition to hold. If Monday's doctor doesn't treat him, Billy's for sure alive. There's no way that he's dead. Okay, are we together? So MT equals 1 is not a cause of Billy's being alive. Now what's the conclusion? We have A causing B, B causing C, but A doesn't cause C. So here's the A, Monday's doctor treating him, is a cause of Tuesday's doctor not treating him, B. Tuesday's doctor not treating him, B, is a cause of Billy's being alive, C. So A is a cause of B, B is a cause of C, but A is not a cause of C. So this definition of causality is not transitive. Now, by and large, I think philosophers today think that that's a feature, not a bug. There are lots of examples in the philosophy literature, this is one, of situations where where causality is not transitive. We get A being a cause of B being a cause of C, A is not a cause of C. Now, interestingly, Lewis's definition of one back in 73 forces transitivity. He defines a notion of direct effect and takes causality to be the transitive closure of that. So you automatically get the causality is transitive. If A is a cause of B, B is a cause of C, then A is a cause of C under Lewis's definition. So most people at this point, I think it's fair to say, think that Lewis's definition is not right because all the examples that show the causality is not transitive, and people buy those examples, this is one of them, are arguments against Lewis's definition. Now, Lewis's definition also forces what logicians call right weakening. If A is a cause of B and B implies B prime, then A is also a cause of B prime. Right? So if you weaken the B to B prime, that's the right weakening, and A is a cause of B, then A is also a cause of B prime. This definition does not satisfy right weakening. MT equals 1 is a cause of BMC being 0. Monday's doctor treatment, or Monday's doctor treating him, is a cause of Billy being okay both Tuesday and Wednesday, but it's not a cause of Billy being alive, which is BMC equals 0, 1, or 2. But surely BMC equals 0 implies BMC is 0, 1, or 2. So A is a cause of B, B implies B prime. A is not a cause of B prime. So causality fails right, this definition of causality fails right weakening. And again, I think most philosophers at this point think that that's a feature, not a bug. But this is what I mean by, we have examples in literature, there are tons of examples. This is, one of the examples that shot down Lewis's definition, because people think that causality is not always transitive, and Lewis's definition forces transitivity, then Lewis's definition can't be quite right. Now, I have, and I think many of us have, the strong intuition that causality sure seems transitive most of the time. So just as an aside, I have a paper that tries to explain why causality is often transitive. So I give a sufficient condition for causality to be transitive, which I think arises a lot. So that might be a reason why we tend to think causality is not transitive. So in other words, one can construct examples like this one where causality is not transitive. So I think it's fair to say that most philosophers now accept the view that transitivity is not a property of causality. But these examples are few and far between, right? I mean, it's not easy to construct an example where you don't get transitivity. And so if you like my paper is an attempt to explain why. But that said, I don't have transitivity. Here's another property that sort of is an argument against my definition that I buy to some extent. This is from a paper due to Josh Knobe and I don't know what Fraser's first name is, but Josh is in the philosophy department at Yale and has a cross appointment to the psychology department because he does what he calls experimental philosophy. So he does philosophy, but also does experiments on people. And here's one of his experiments. So here's the story. The receptionist in the philosophy department keeps her desk stocked with pens. The administrative assistants, the secretaries, are allowed to take the pens, but faculty members are supposed to buy their own. They get good salaries, they can buy their own pens. In practice, both the secretaries and the faculty take the pens. So in this particular Monday morning, an assistant and a professor both take pens. Unfortunately, there were only 2 pens originally. So when the receptionist needed to take a pen later, needed to write a message later, there were no pens left on her desk. So both the assistant and Professor Smith took a pen. There were only 2 pens. Now when the receptionist needs a pen later, who is the cause of there not being a pen? Now, according to our definition, this is completely symmetric. Each of the assistant and the professor are but-for causes of there not being a pen. Had the assistant not taken a pen, there would have been a pen there. Had the professor not taken a pen, there would have been a pen there. So each of them is a cause separately of there not being a pen, because a but-for cause, because had they not taken a pen, there would have been a pen there. Right? So there's nothing really deep going on in this case. Yet, when you ask people, most of them don't say both of them are causes. They say Professor Smith is the cause. Why? Well, where's the asymmetry? Well, this is the only sentence that has asymmetry. Administrative assistants are allowed to take pens and professors are supposed to buy their own. So this sentence introduces an asymmetry between admins and faculty members. Although I claim, the next sentence tells you statistically there's no asymmetry. They both take pens all the time. So this suggests there's more to causality than just the structural equations, because as far as the structural equation goes, they're both causes. But nevertheless, as Danny Kahneman in a paper with Miller, so Danny Kahneman won the Nobel Prize for his work on what's now called behavioral economics, also studied causality with Tversky. There's a wonderful paper with Kahneman and Tversky where they looked at causality. In a later paper with Miller, he wrote the following, or they wrote the following: an event is more likely to be undone by altering exceptional rather than routine aspects of the causal chain that led to it. What is he saying here? That when you're trying to think of something as a cause, you're thinking about the counterfactual. Suppose it weren't the case. You're more interested in counterfactuals that change intuitively abnormal things to normal things. When you're thinking about what's the cause, you're more likely to try to change the unusual event rather than what always happened, right? When you sort of think, I got stuck in a traffic jam yesterday. I don't normally get stuck in traffic jams. Why did I get stuck? Well, it's because I took the highway home instead of going on the back roads. That was the cause, right? Because you look at what you did that was different. You look at the unusual event typically when you're trying to find causes. And so we would argue that the reason that most people choose Professor Smith as the cause is he broke the rule. The rule said that faculty members are supposed to buy their own pens, and whereas admins are allowed to take pens. So you're making the world more normal by undoing Professor Smith taking the pen, because he's not supposed to take the pen. It wouldn't make the world more normal if you undid the admin taking the pen. So that's the intuition. I won't allow time for questions, so I won't go through the formal definition, but intuitively, this is work I did with Chris Hitchcock. We put what we call the normality ordering on worlds. This had been done before in AI to capture default reasoning. So this is a standard approach in AI to capture not causality, but default logics and so on do this. And the idea is I have, the world intuitively in this case, the world where Professor Smith doesn't take the pen and the admin does is more normal than the world where Professor Smith takes it and the admin doesn't. So when I'm looking, the intuition for the modified definition, once I have normality, is if I'm going to look at the counterfactual, if I'm going to change something, I prefer to move to a world that's a more normal world. So I prefer to change Professor Smith to not taking a pen than the admin to not taking a pen, and that's why I'm more likely to call Professor Smith the cause. And indeed, what happens if they change the story and say admins are not supposed to take pens, they're for the faculty. Admins have another way of getting pens. Then everybody says the admin is the cause, not the faculty member. So it's clearly this sense. Yeah, sure, go ahead.
Quick question. So my intuition is, they both the cause, but Professor Smith is to be blamed.
Interesting. I'm going to talk about blame in 4 or 5 slides. So stay tuned. We'll talk about blame.
Okay.
And it's certainly the case. So Yanchik, that's actually very interesting for 2 reasons. One is these issues come up in the law. And one lawyer I spoke to said, I prefer not to change your definition of causality, but rather talk about blame. The other thing I will say is that people, when you ask people, and that's the trouble with these experiments, people tend to confound the notions of causality, responsibility, and blame. So you have to be a little bit careful. So I claim here's one way of capturing the phenomenon, but I'll talk about blame in a second. Right. So let me just briefly mention that when we talk about normalities, so here we have an abstract model. I'm not going to go into details, where we just have a normality ordering on worlds. Right? As part of the definition of the model, I'm going to say this world is more normal than that world. Right? That's a standard move in philosophy. So, this is part of the semantic model. It's a subjective definition of what counts as normal. Now, in practice, what does it mean? Does normal mean it's statistically frequent? Right? Things, birds typically fly, but there's some birds that don't fly. Right? So that statistically, if you take a random bird, it flies, but definitely there's some birds that don't fly. Baby birds don't fly, ostriches don't fly, emus don't fly, but most birds fly. So certainly it's the case in English when we say typically birds fly. One interpretation of that that's not unreasonable is that the great majority of birds fly. sometimes when we say typically, we don't even mean majority. I mean, somehow if I think of the prototypical lion, it has a mane, right? It has sort of hair, right? These are the standard pictures of lions. But as it happens, female lions don't have manes and younger lions don't have manes. So statistically, the majority of lions don't have manes because none of the females do and none of the young do. Nevertheless, we think of having a mane as a typical property of a lion. And English, people have tried to get a theory of typicality and that's not statistical, right? So if I think of the prototypical lion, it has a mane, even though statistically most lions don't have manes. Another interpretation of typicality is conformance to a norm, and that's what I think was going on here, right? That the norm is that faculty members are supposed to buy their own pens. Another interpretation of normality is, morality. It's thou shalt not kill. It's very abnormal to kill. And people typically consider all these notions when they're looking at normality, and by and large, conformance to a norm seems to trump statistical frequency. So in this case, as far as statistics go, statistically, assistants are just as likely to, as professors to take pens, but nevertheless, when I think about normality, this takes precedence. That or at least it seems to when you talk to people. But it's sort of interesting to think about psychologically and philosophically what counts as normal. Okay, so Yanjing raised the issue of responsibility and blame. Let me say a few words about that. It's only going to be very few, but so the definition of causality can be extended to deal with responsibility and blame. They're different. Now, again, English conflates the words, so I'm going to use responsibility and blame for two different notions. The intuition is the causality is a 0 and 1 notion, either A causes B or it doesn't. We can extend to talking about the probability that A causes B. We can do that by putting a probability on context. So we can look at the set of contexts where A causes B, the set of contexts where A doesn't cause B. And so we can talk about the probability that A is a cause of B, but that's not what I want to get to here with responsibility and blame. It's not at least responsibility is not a probabilistic notion. So here's an example. Suppose B wins an election against G. This is in the days of Bush and Gore by a vote of 11-0. So intuitively, each of the voters for B is part of a cause of B's winning. But again, intuitively, you feel a lot more responsible if the vote is, the 6 voters who voted for feel much more responsible if the vote is 6-5 than if it's 11-0. If it's 11-0, you say, well, don't blame me. He would have lost anyway, even if I changed my vote. Whereas here, say, oh, I'm critical. If I change my vote, the result changes, right? So I want to capture this distinction. And this is not probabilistic. And we have a naive definition, and so we can model this formally. And the intuition is your degree of responsibility is 1 over K if K is the size of the smallest set that will flip things. So in this, and you're part of it. So in this case, K is 6, right? So that to what extent are you responsible? Well, you have to flip 5 votes. And then if you're the 6th vote to flip, that'll change it from 11-0 in favor to 6-5 against. So we would say your degree of responsibility is 1/6, 1 over 6, because it takes 6 votes before things are different. Now, in general, your degree of responsibility is 0 if you're not a cause, and it's somewhere between 0 and 1, strictly greater than 0 and less than or equal to 1 if you are a cause. So in the case of the 6-5 vote, your degree of responsibility is 1, because all it changes is 1 person to flip and the outcome changes, so it's 1 over 1. And in the case of the 11-0, we say each of the voters has degree of responsibility 1/6. So it's not like probability, it doesn't add up to 1. So here, each of the 6 people who voted for him have degree of responsibility 1. The total degree of responsibility is 6. In the 11-0 case, all the 11 voters that voted for have degree of responsibility 1/6. So again, it doesn't add up to 1. I'm not going to go carefully through the formal definition because I want to get to the end, but let me just mention that this is not probabilistic, but sometimes we want to take probability into account. So assume you're uncertain. So think about the following case. Suppose a doctor uses a drug to treat a patient. And suppose, in fact, that drug is the cause of death. Well, then you say, okay, the doctor has degree of responsibility 1. If he had done something different, the outcome would have been different. So he's the cause and he's critical, so degree of responsibility 1. But suppose the doctor had no idea that there would be adverse side effects. Then the law might say that he's not to blame. And I want to capture that. Now, I should say as an aside, well, actually, let me give you the formal definition, and then I'll come back to this slide. So intuitively, here's the idea. Consider a firing squad with 10 excellent marksmen. One of them has a live bullet, and the rest have blanks. And this is the kind of thing that actually happens. If you sentence somebody to die, then only some of the shooters have, if you're doing it by firing squad, not all of the rifles have live ammunition. So suppose in this case there are 10 marksmen, only one has a live bullet, the other 9 don't. They shoot, they're all perfect shots, they all shoot, the guy dies. Now, the only one who's a cause of death is the one with the bullet. None of the rest are causes. There's no counterfactual but for. If they hadn't shot, doesn't make any difference. They don't have a bullet, right? So the one guy who has a bullet is the cause. That one guy has degree of responsibility 1 for the death. He's critical. All the rest have degree of responsibility 0. There's nothing they could have done about it. They're not causes. They don't have a live bullet. But each marksman has degree of responsibility 1/10. So formally, I'm not going to write down the formal definitions. The degree of blame is the expected degree of responsibility. So now I'm assuming that you have a probability distribution over contexts, actually a probability distribution over context and models, because you might not be certain what the right model is. Does smoking cause cancer or not? So you have a distribution over pairs consisting of models and contexts. In each such pair, you have a degree of responsibility, and your degree of blame is your expected degree of responsibility. Multiply your degree of responsibility times the probability. So for example, here, each marksman considers 10 such pairs possible. They all know what the model is, but there are 10 possibilities. Number 1 has the live bullet, number 2 has the live bullet, number 3 has the live bullet. Each one has probability 1/10. So for each marksman with probably 9/10, they're not the one with the bullet, so they have degree of responsibility 0. And with probably 1/10, they have degree of responsibility 1. So their expected degree of responsibility, which is the degree of blame, is 1/10. Does that make sense? Now I should say here that in legal reasoning, this definition is relative to what we call the epistemic state. And in this case, the epistemic state is a probability distribution over models and contexts. Now, the definition doesn't tell you which distribution you should take. And at least in the US, the law says that you should take the distribution of a reasonable person. So in other words, if the doctor says, I had no idea that the medication would have caused problems, but there was an article in the New England Journal of Medicine, which is a major journal, that said this medication causes problems for people with heart disease, then the law would say you should have known. Or even more so, if the drug manufacturer had put something, usually have on the drug or a piece of paper in the box that says, here are some contraindications. You shouldn't take the drug if you have a heart condition. Now, maybe the doctor, in fact, didn't know because he didn't read. He didn't read the article or he didn't read the instructions. But the law would say that's no excuse. So basically, the law is taking your epistemic state not as your actual epistemic state. Maybe, in fact, the doctor had no idea. But the epistemic state that you should have had if you'd been a reasonable doctor and read everything that you should have read. So the definition, when I say the degree of responsibility is your expected, degree of blame is your expected degree of responsibility, that's relative to an epistemic state. And, we can figure out, the law might say, this is what epistemic state we're going to use. I mean, the definition, you can sort of plug in the epistemic state into the definition. So let me quickly, I won't spend time talking about computer science applications or complexity. The problem of determining causality is NP complete for those who care about these things. But let me just conclude, so we'll have a few minutes for questions. The trouble with people. People don't always agree on descriptions of causality. People apply multiple intuitions for inferring causality. They conflate notions like responsibility and blame and causality. But nevertheless, so I did, mainly Toby Gerstenfeld, who at the time was a postdoc of Josh Tenenbaum's, but is now a professor of psychology at Stanford, did a bunch of experiments with voting scenarios on Amazon Turk. And we did show, so this is the engine, this is in part, answering your questions, that the degree of responsibility, our definitions actually really were quite good at predicting how people would act. And we also showed that people were their responsibility ascriptions were affected by normality as well. So we did things like we said, okay, if the vote is 2 to 1 or 3 to 1, your degree of responsibility is less than if the vote is 2 to 1. So people agreed with that, just like our definition. But suppose there's a measure that's supported by the Republicans and not supported by Democrats. And now it's supported by the Republicans. 2 Republicans vote for it, a Democrat votes for it as well. Who's more responsible for it for passing? People say it's the Democrat because he did the abnormal thing. So when they're assigning degree of responsibility, they are taking apparently normality into account. So let me just conclude and say, look, when you ask somebody what's the cause of something, there's lots of examples that people can give different answers. So I say, what's the cause of the traffic accident? The engineer might say, oh, it's a bad road design. The mechanic might say, bad brakes. The sociologist might say, nah, come on, there was a pub near the highway, the guy drank. That's why he had the accident. And a psychologist might say, why did he drink? He was depressed. He just broke up with his girlfriend. That's the cause. If he hadn't been depressed, he wouldn't have drank, he wouldn't have had the accident. Now, I'd like to say all these answers are reasonable. And the way we would capture the difference is it depends on what you make exogenous and what you make endogenous. And what people do in practice is we make exogenous the things that we can't control, and we make endogenous the things we have some control over. So think about the engineer. The engineer he thinks a lot about the road design. So he wants to make that endogenous. The fact that there's a pub near the highway, well, that's just the way it is. That's exogenous. That's the world as given. The psychologist, on the other hand, would make endogenous the fact that the driver was depressed because that's what he feels he can do something about. So what I want to point out here is that the choice of model matters. What you make exogenous and endogenous matters. And typically, that when we model things, what we make endogenous are those things that we feel we can do something about, because that's why we care about causality. I want to know that A is a cause of B in large part because what can I do to stop B from happening, right? So now, is this the right definition? I don't have a theorem that says this is the right definition. I wish I did. I think it's a useful definition. So it's certainly possible that tomorrow somebody will come along and come up with an example and I'll say, okay, I'm convinced this is a bad definition. This example killed my definition. I would still argue it's useful. So I didn't talk about applications in computer science, but this definition has turned out to be quite useful in computer science applications. I hope it'll prove useful in the law. What that means is even if somebody finds a counterexample, I think philosophers are very focused on counterexamples. I'm enough of a computer scientist to say I'm also interested in applications. So it turns out this definition is useful. So even if it has counterexamples, that people have used it and it seems to help them in reasoning about programs and reasoning about security and so on. And I'm expecting that a lot of the research agenda is going to be driven by examples. I think causality, for example, is critical for things like fairness. I think this model can be really useful, even if it isn't the perfect model, even if it isn't the right model. So let me stop there. I hope we still have a few minutes for questions, and I hope it made some sense. So,
yeah, thank you very much, Joe. So
the sound of one hand clapping.
yeah, I think we can have a few more minutes for questions, especially from the attendees. So yeah, you can either just raise your hand or type your questions in Q&A.
So in the meantime, can I again ask a question?
Sure, go ahead.
Yeah, so, okay, so I think, I mean, this definition of causality is pretty much depending on how you do the model, right? You do the modeling.
Absolutely.
So I'm thinking how to understand better how much modeling will affect this thing in a technical way.
That's a very good question.
Yeah, I think I have one suggestion where possible approach is to find a sort of structural equivalence between your causal models, like those equations. Can you prove something like in modal logic we have bisimulation for modal language? In this case, can you show that modulo some kind of equivalence between those equation systems? You don't really change the formula. Yeah.
You can define an analog to bisimulation. Let me tell you, to me, well, here's the concern, and here's an issue that arises that philosophers, I think, need to look at much more. So suppose I keep adding, I keep refining the model. So now they're not going to be bisimilar. I'm adding more variables to the model, right? Because I discover more and more things matter. But somehow I'd like to suppose one model is what logicians call a conservative extension of another. So although I added more variables, at least on the old variables, things haven't changed.
Yeah.
Can the definition, can the fact that A is the cause of B, can that change? The answer is, if you're not careful, yes. I have some sufficient conditions that guarantee this kind of a stability property that refining a model won't affect anything. Sander Becker has done some very nice recent work on extending, getting even better definitions of stability and proving some theorems along those lines. But that would be the kind of thing that I would worry about. It doesn't bother me that in general different models give different answers, but somehow I'd like to say, well, you know, if you keep refining the model so you can talk about more things, but somehow that shouldn't change what happened among the old variables. To what extent is that true? And that turns out to be delicate, right? So that is an issue to worry about a lot, I think. And it's an issue, as I said, the philosophers have not really looked at. In my mind, they haven't looked at it at all, except for my paper and now this recent paper of Sanders. And I think it's an issue that deserves a much closer look. Even if you don't like my definition, I think this issue of stability is important to think about for other definitions.
Right. Okay, thanks.
Other questions?
May I ask a question too?
Sure.
Hello. Yeah. I was wondering. I'm a linguist, so I didn't fully understand the logical modeling here. But I was wondering whether the distinction between subjective causality and objective causality play a role here, because we as humans could make all sorts of causal reasoning or causal inferences, which might be true or not true. I was wondering whether you are.
I don't have a notion of subjective and objective. For me, causality is always relative to a model. Now, you can certainly ask, is this a good model of the world? Right? So that it's the modeler constructing a model. So I suppose in that sense, everything is subjective, but we can certainly test the claims of the model objectively. So, you know, the model has the equations, right? The model is saying, if I throw a rock, the bottle, if Susie throws a rock, the bottle will shatter. Is that true? So we can check whether the equations accurately describe the world. And the closer they are to describing the world, I suppose you could say that, that makes the model more objective in some sense. Well, I wouldn't use the word objective, I would use the word accurate, right? So I don't have any notion of objective and subjective, I mean, like probability. Is there a notion of objective probability? I'm not sure. I mean, some people would argue probability is always subjective. That's an issue I frankly would rather avoid. And so I haven't used the word objective and subjective at all in this talk, except maybe I can talk about the agent's epistemic state, which is the agent's probability on, the agent's belief about how close various models are to describing reality. But it's certainly important if you're going to use these definitions of causality, let's say in the law. Well, you want to argue that the model you're using is an accurate reflection of the world. And that's something that to some extent you can test. I mean, when I write down equations, are these equations, do they correctly describe the world? Now, again, I'm not sure I would use the word objective, but I certainly would want to be able to verify that the claims that the model is making are accurate, right? I mean, I can imagine two lawyers arguing a case. One lawyer says, my client is not the cause of this accident, and presents a causal model. The other lawyer presents a different causal model and says, well, my causal model, your client is the cause. So now somehow the jury has to be able to decide which model more accurately reflects reality, right? But I think we can do that, right? We have equations. We can see if the equations are an accurate reflection of reality. A context has claims that x equals 3. Well, is it true that x was 3? You might not know. In other words, is it true that you were drunk? That's a fact about the world. So the model would say, well, if you were drunk, you're the cause. But then we have to check in the world if it's true that you were drunk. So I'm not sure that I've answered your question, but as I say, certainly if you're going to apply this in the law or to make statements about a computer program, you certainly would want to check that you have a good model, that in some sense your model is accurately reflecting the situation you care about. And I would say, for example, this model is a bad model of the story that I gave with Susie and Billy throwing, because it doesn't capture the fact that Susie threw harder and therefore hit the bottle and Billy didn't. So it's a different sense of bad. Even if you say, well, it's true that Susie threw and it's true that Billy threw and it's true that the bottle shattered, so all the statements that the model is making are correct, I would still say it's a bad model because it doesn't have enough variables to accurately reflect what the story told me. So it's a bad model of the story. And I think lawyers, even if they use the formal definition, will still have to argue that their model is a good model. And we need an understanding of what makes a model a good model. So Chris Hitchcock and I wrote a paper about that, but again, I think there's a lot more to be said, and it's something that philosophers and maybe linguists need to worry about more, sort of coming up with criteria for what makes a model a good model.
Okay, Joe, there's also a question in the Q&A.
Okay.
Yeah, the question says, can you please clarify how the definition you presented today is better than your previous ones? Yeah,
so it's better than the first one because in the first one, there are examples that didn't work well. It handles those definitions well. So I have, in my book, I have a few other examples that the last definition seems to work better than the first two. The last definition also has the merit of being simpler. I mean, it might not have looked that simple to you, but trust me, it's a lot simpler than the second one. In terms of complexity theory, I didn't really talk about this, but to a computer scientist, checking whether A is a cause of B in this case is what's called NP complete. That's not great, but it's even worse in the other definitions. They have higher complexity. So again, these are different ways in which I think the last definition the last definition also has the property of stability in more circumstances. This is the thing I was saying to Yanjing, that if you add variables, the question of whether A is a cause of B, that doesn't change. That's true with the last definition, not so true with the first and second definition. So there are many ways in which I think that the last definition is better than the first two, but again, that doesn't prove that somebody won't come along and come up with an example that I'll find devastating and say, oh, okay, still not quite there.
Okay, great. And there is one more question in the Q&A, and for the sake of time, probably this is our last one. So can you actually, Joe, can you read it in the Q&A? It's a bit long.
Just a minute, so I don't have, just a minute.
Okay, sure.
I have to get it on my screen. Q&A, yes, I can.
Okay,
It
great.
says, what I'm seeing is no open question, no open questions.
In the answer list, I put it in the answer list. Yeah.
So I see two questions. I see one from Luis, which
Yeah,
I guess I answered. In the Susie Billy case, it seems the BS equals 1 picks out the same event with either SH equals 1 or BH equals 1. I don't know what you mean by picks out the same event. I don't know what it means to pick out an event, so I don't know how to answer that question.
Yeah, I guess probably the worry here is that there may be some kind of logical relationship between the variables here. So maybe just logically speaking, BS is equal to 1, just in case HH is equal to 1 or BH is equal to 1. I mean, I guess that's the intention
That's
here.
what the equation says. I don't know what it means to pick out the same event again. It's true that we get, I mean, the equation says if either SH equals 1 or BH equals 1, then if you like, under normal circumstances, BS equals 1. But that's just a fact about the world. I mean, I don't know how to answer that. So I'm just saying that if either Susie throws or Billy throws, if either Susie hits the bottle or Billy hits the bottle, then the bottle shatters. So I'm saying something that this is not, it is a fragile bottle. If a rock hits it, it'll shatter. You know, one can imagine that there are bottles that are built of, you know, steel, that even if the rock hits them, okay, they fall on the floor, but they don't shatter. So here I'm just making a claim about the structural integrity of the bottle, that if either rock hits it, then it will shatter. If that violates a philosophical requirement, I would say the philosophical requirement is in trouble. Now, in terms of independence, it is the case that I'm implicitly assuming in this model, the structural equations model as I've presented it, implicitly assumes that you can arbitrarily intervene on variables, which means that they're independent, logically independent. So you can arbitrarily intervene and set SH equals 1 and BH equals 0 and BS equals 0. That's okay. I mean, you can intervene and say Susie hits and Billy doesn't, and nevertheless the bottle doesn't shatter. There are two, if you think there are logical connections between the variables, so you can imagine a variable that talks about weight in kilo and weight in pounds. So as a logical fact, if it weighs 1 kilo, it weighs, let's say, 2.2 pounds, or more or less, right? And then it seems very weird to intervene and set the weight in kilo to 2 and the weight in pounds to 18. I mean, because that's logically inconsistent. So I have a paper with Chris Hitchcock and Sandra Beckers that extends this definition to allow models that have logical relations between variables. This is not such an example. I don't view SH, BH, and BS as being logically related in the same sense that you know, weight in pounds and weight in kilo are related. But doing that ends up adding a lot of subtleties. So, you know, this was meant to be a brief overview of my work in causality, but I have many, many papers and I can't possibly summarize them all. So that is recent work I've done with Chris and Sander. Another way I would, that's a sort of a less drastic extension of the model, is that we can also limit the interventions you can do. We can say as part of the definition of the model, you're not allowed to intervene to set X to 3. That's just not, or you're not allowed to intervene to simultaneously set the weight in pounds to 18 and the weight in kilo to 2. So we could just say that some interventions are not feasible. And so part of the definition of a model is, you know, what are the feasible interventions? So none of the definitions change, but you just have to restrict everything to feasible interventions. So if you like, two different ways of dealing with, lack of independence, but I'm not quite sure if I've answered the question, but maybe I've given some sense.
Yeah, I think so. Yeah, I think that was the question, right, about the possibility of having logical dependence between the variables. So thank you, Joe, very much for the
You're welcome.
and so I think our seminar ends here.